Hey guys, welcome back. I'll just uh, once again re-explain you the open collector output and the tri-stating output just in brief because I already completed that in the last lecture, and I'm just opening the diagram. Uh, yeah, perfect. See, it's very simple. It's very simple. Say for example, if any of these two devices, say for example, maybe device one wants to signal the interrupt. Okay, it wants to signal the interrupt. So it says it drives its input to low. Okay, it drives its input to low. So when any of the devices wants to signal the interrupt, they drive their interrupt output. Sorry, they drive their interrupt output to low, and this signal will also go low. And then the microprocessor will respond to this interrupt signal. Got it? If say for example, if this chip 2 wants to interrupt the signal, it'll interrupt the output signal as low, then even this goes low, then the microprocessor responds to that particular signal. See, if neither of these devices wants to signal the interrupt, okay, each will let its output float. Float means there is no signal, there is no output from that particular device. So many people ask me a question, so what do you mean by the term, or what do you mean by the output is a floating signal? A signal that no output is driving is called a floating signal. You can write this down, make a note of it. A signal that no output is driving is a floating signal. Perfect. Yeah. If say for example, if neither of these devices wants to signal the interrupt, then each will let its output flow. Now comes this pull-up resistor. So this pull-up resistor will cause this particular int to go high. Okay. Then if it goes high, then the microprocessor will sense that acha interrupt input is not asserted. Interrupt input is not asserted. So pull-up resistor is a very important part in this circuit. Okay. And it is necessary, it is very much necessary for this particular circuit to work. Okay, because the signal would float, that is, it wouldn't show anything if neither of these devices wanted to interrupt. Okay, the pull-up resistor uh, goes high, so makes this int high in this particular situation when neither of these devices want to interrupt the signal. Okay, got this is regarding the open collector output. Just remember, in general, I'll just tell you the difference between a tri-state output and an open collector output. Just don't confuse, it's very easy. In general, when you have standard parts, or either like they drive their output signals as high or low, open collector outputs drive their signals low, or they allow them to float, or they let them to float. So open collector outputs drive their signals low, or they let them to float. Another class of outputs, they drive their signals either high or low or float. These are called the tri-state outputs. Okay, these are called the tri-state outputs. I'll show you the picture of a tri-state output also. This is a circuit using a tri-state driver. Okay, say for example, a tri-state driver would work in such a way, and says any select signal is asserted, then the tri-state driver output will be the same as the input. Okay, got it? See, this triangular symbol in the schematic is called the tri-state driver. You can just make a note of it. This is called the tri-state driver. Perfect. So it works in such a way that when the signal, or when the select signal is asserted, then the tri-state driver output will be the same as the input. Say for example, if select A is asserted, and select B and select C are not asserted, okay, then the tri-state driver A can drive the output signal high or low. It's like based on what is the input. Okay, if say for example, if the input, or if the select signal is high, it gives us an output as high. If the select signal input is low, it gives us output as a low. And drivers B and C, I'm just sorry because the picture got cropped. there is a C here. It is very simple. You can add up an input C like this, okay, and place some tri-state driver here and connect its output to this particular dot. So it's similar. So the output signal here, the important point is the output signal will reflect the input of the driver for which the select signal is asserted. Okay, the outputs, I'm just repeating it again. The output signal will reflect the input of the driver for which select signal is asserted. Okay. Say if input A signal is not attached to select B or C, if input A is not attached to select B or C, or select or input B is connected, not attached to select A or C, in such a way, you can even you know have those all kinds of permutations and combinations while you are connecting it to the particular driver. So you can see the dot here, right? You can see the dot here, right? So here the three tri-state driver outputs are intersecting. Okay, because I want a combined output. That's the reason all the three tri-state drivers outputs are intersecting. Okay, the usual convention in the schematic is that two cross lines on schematic are not connected without a dot. Say for example, see, as I was telling you, select A is not connected to input B or A with a dot, or select B is not connected to input C or input A with a dot, but the outputs, the tri-state driver outputs are connected with a dot and the common output is taken. This is what happens in the case of a tri-state driver. You got it, right? So this is one of the important concept, and then I'd like to take up on the memory. Yeah, memory is very simple, guys. You can just read it by yourself. There is nothing new in case of a memory. You have a read-only memory and the random access memory. I'll just give you a brief introduction. Most computer systems use some variant of read-only memory or the ROM. It's called RAM basically. It's pronounced as RAM. See, the microprocessor can read the program instructions from the ROM quickly and typically as fast as the microprocessor can run the program. So reading the instruction and running the program is being happens simultaneously. Okay, the microprocessor cannot write new data to the ROM. Right, I'll just make note of all these points if possible for you guys so that you can happily write them in your exam. Read only memory. Okay, so the first point which I would like to make note is the microprocessor. I told you, right, the microprocessor can read the program instructions from the ROM quickly. Typically, as fast as the microprocessor can run the program. Okay, just go through this point. See, the microprocessor can read the program instruction from the ROM quickly, typically as fast as the microprocessor can run the program. Okay, next would be my next point is, this is also a very good important point. In the second point is, see, the microprocessor cannot write new data. It cannot write new data to the ROM. Okay, it cannot write new data ROM. That is, the data is unchangeable. In brackets you can write data is unchange, CHANG. The data is unchangeable. Got it? Perfect. See, the good point here is the ROM remembers the data even if power is turned off. Perfect. So these are some of the important points regarding the ROM. And yeah, see what happens is I'll just give you a glimpse. When the power is turned on in general, the microprocessor will start fetching the program from the ROM. You try to make a note of it on your own. When power is turned on, the microprocessor will start, getting the data from the ROM. Okay, the signals, you can just go through this ROM chip schematic symbol. ROM chip schematic symbol. I'll just try to find it out for you. If I find it, or else I'll post it in the resource section. I'll add some resources to you with this link possible. It is ROM chip ROM chip schematic diagram. I think this would do good with this. Yeah, this is fine. This is fine. Uh, uh, yes, I'll just make a note of this ROM chip schematic diagram. I'm just trying to find out a very good diagram so that you guys can understand. Uh, okay, let's do one thing. I'll just give you the previous diagram itself. Just let this be the previous diagram. Instead, here, oh sorry, yeah, here on this side you'd be having the address lines, that is A0 to AN. Here, instead of these, you have the address lines A0 to AN. Okay, which indicate the address from which the processor wants to read. The address from which the processor wants to read. Okay, it indicates the address from which the processor wants to read. And the number of these signals depend on the size of the ROM. Okay, you depends on the size of the ROM. In case if there is larger ROM, you definitely need more address lines. Okay, and on this side, the signals from D0 to DN, that is the data signals. There are typically 8 or 16 of these, and here you can have a CE signal, that is the enable signal, which tells the ROM that microprocessor wants to activate the ROM. It is sometimes called chip enabled signal. It is called chip enabled signal. That is in the bottom. Yeah, here you can keep it here. Chip enabled signal. Okay, this tells the ROM that the microprocessor wants to activate the signal, and the ROM ignores what happens is the ROM ignores the address signals unless the chip enabled signal is asserted. Only if the chip enabled signal is asserted, then the ROM gives importance to the address signals. Okay, and here you can put one more thing called as read enable signal. It is also called as output enable. Okay, unless the chip enable and read enable are asserted, the ROM tri-states it output data signals. The ROM tri-states it output data signals. This is regarding the ROM. Okay, I mean the the diagram is not exactly like this. What I did is I'll just put lines like this, and A0, A1, A2, so on AN. Okay, and here you can have your chip enable, and here you can have your read enable, and on the right side you can have your data signals. This is regarding the ROM. There are many ROM variants. You can have to go through the ROM variants. One is PROM, the programmable read-only memory. Then the EPROM, the erasable programmable read-only memory. I'll write these. Just go through the definitions of the ROM variants. Okay, first one is PROM, second one is EPROM, third one is EEPROM. Okay, EEPRO. First one is programmable read-only memory. The second one is erasable programmable read-only memory, and the third one is electrically erasable read-only memory. Okay, good. So these you can just Google them. You'll just find simple, easy definitions for these. So say I'll just explain you each very quickly. So PROMs, okay, PROMs, you can write a program into them in your office with a PROM programmer, or you'll have a PROM burner. Okay, it is basically a tool which is made for this purpose. Okay, it is very simple writing a program into the PROM, but you can write into the PROM only once. If it has a mistake, you have to throw the PROM away. You have to fix the program and write the new program on new PROM. That is, you can, once you write it, you have to make sure that you write exactly. So PROMs mostly are not advisable. The writing program is easy, but if it has a mistake, you have to throw away the PROM. And the tool which you use to write a program is called PROM burner or PROM programmer. The next variant is EPROM. You can erase them and reuse them. That is a simple difference between these two. The usual way to erase an EPROM is to you can shine a strong UV light on top of the chip. There is a small window, and on top of the chip, EPROM erasers. Okay, EPROM erasers boxes with UV in them. So you use a UV light, and they're in fact widely available, and they're not much expensive. They're inexpensive. Then even the flash memory. Yeah, I forgot to mention the flash memory. Flash memory. This is also a very good example. EPROM, 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 and EPR. Yes, perfect. So you can go through the RAM and ROM properties and their in stuff in Google, because you're learning what is a RAM, what is a ROM right from your childhood, right? So I'll not waste much time on it. And the most important thing are the timing diagrams. They show the timing relationship among events in a circuit, right? And one of the most important thing is, I hope you learned about flip-flops. D for Delhi. D flip-flops are 1-bit memory devices. This is a very important point. D flip-flops are 1-bit memory devices, right? Perfect. Yeah, I think I'll now move on to the bus. I'll just move on to the next thing, that is preferably the buses. Okay, I'm just covering the entire unit. These are also the individual components. Perfect. See, it is very simple. I'll just go through it. This is how you construct a very simple system from just a microprocessor, a RAM and a ROM. Suppose that it has 3: CPU, RAM, ROM. I'm constructing a very simple system. I'm constructing a simple system using CPU, ROM, and RAM. See, all these three have 8 data signals: D0 to D7, D0 to D7, D0 to D7. So 0 to 7, total 8 data signals. The microprocessor can address 64K of memory and have 16 address lines. See, A0 to A15, A0 to A15. The ROM and RAM each have 32K. So that's the reason they have 15 address lines each. A0 to A14, A0 to A14. Got it? See, A0 to A14, A0 to A14. And this is A0 to A15. And this is a schematic of a system which we're going to construct. Okay. The address and the data signals on the microprocessor are connected to the address and the data signals on the ROM and the RAM. Okay. The read signal from the microprocessor is connected to the output enable on the memory chips. And the write signal for the microprocessor is connected to the write enable on the RAM. So see, you can find this link, right? The read is connected to the output enable on the ROM, and the write is connected to the write enable on the RAM. And some kind of clock circuit is attached to clock the signals on the microprocessor. It's pretty much simple. See, the address signals as a group are very often referred to be address bus. The data signals as a group are referred to be data bus. Simple, you understood what is an address bus? Address signals in a group is called an address bus. Data signals in a group are referred as data bus. So the combination of these two plus perhaps the read and write signals are referred to be a microprocessor bus, or it is a bus. This entire setup is basically a bus. Okay. How does this circuit deal with the fact that the microprocessor might want to read either from RAM or from a ROM? See, it's very simple. Microprocessor doesn't know there is something like a RAM or a ROM chip. It just has 64K address space, and when it drives address signals on the address bus to represent one of the address in the space, it expects someone to provide data signals, someone to provide the data signals on the data bus. To make sure that the microprocessor can read, you must divide the address space, assigning some to the ROM and some to the RAM. Then you must build to implement your division. Since the ROM and RAM each have 32, one possible division is, say, I'll just show. One possible division might be this diagram. Not this. This is the interrupt stuff. Okay. One possible division is like, say for example, it have the low address. It has the low address. I'll just show you even that picture. It's very simple. It is. Yes, you can see it, right? So yeah, this is a possible division of the address space to the ROM and RAM, right? Because I told you the microprocessor doesn't know what is a ROM and what is a RAM. I'll explain you what goes and how this actually works. See, you can do the arithmetic and see the both of the ranges. Say for example, to use these address ranges, you must build a circuit that activates the ROM chip when address in that particular region appears. And a RAM, see, ROM has a region, say for example, 0 to 10 marks. The people who got 0 to 10 marks in maths sit in the first row, 10 to 20 in the second row, and 20 to 30 in the third row. So the first row range is 0 to 10. So if I get 5, I'll just pick up the first row. If I get 30, I'll just pick up from the third row. In a similar way, if the address region is in the range of a ROM, then the range appears on the bus and that activates the ROM. And if it is in the address region is in the RAM chip range, then an address in that range appears. In this particular case, this is very simple. See, all the address that correspond to ROM are the high order address signals, that is 0. Whereas all the address that correspond to RAM, that is 1. So for ROM it is 0 and from RAM it is 1. You can use the A15 signal, that is the last signal, right? The A15 to decide which of the two chips, RAM or ROM, should be activated. If the A15 is 0, then you can select the ROM. If the A15 is 1, then you can select the RAM. You can see, right, the A15 is attached to the chip enable signal on the ROM. So enabling whenever A15 is 0, and it is inverted and attached to the chip enable signal. Where is the picture which we were talking about? Yes, I think it's this one. Yes. See, the A15 signal is attached to the chip enable. So it is 0. The same A15 signal, here it is inverted. That is, if it is 1, it goes here. See, this is an inverter. If it is 0, after inverting it becomes 1. So it is enabled to it is attached to the chip enable. Right. Say I'll take an example. Consider microprocessor tries to read an address of some 9123. Okay. I'll give you a good example of it as well. Say if the microprocessor wants to read an address, say that address would be some 0x9123. The A15 signal will be 1. Why? Because the 0x9123 binary code is 1001 0001 001 0011. Right. This is binary, which means the chip enabled signal on the ROM will be high. The chip enabled signal on the ROM will be high. Got it? And therefore, the ROM will therefore be disabled. But because the A15 is high, the output of the inverter at the bottom will be low. So A15 is high, the output of the inverter will at the bottom would be low. Therefore, the RAM is enabled. And the RAM will place its data on the cell, whatever address bus would if it is. You got? I hope you guys understood. Right? See, if the microprocessor tries to read from this particular address, it is trying to read from this particular address. The A15 signal will be 1. Why? Because this entire thing is in binary. Is 1001001. The entire stuff is in the binary. It is this equivalent in binary is this. Okay. Since the last position is 1, the A15 signal will be 1. Which means the chip enabled signal on the ROM will be high. Therefore, if it is high, it will be disabled. But A15 is high. When A15 is high, the output which in the inverter, see, this A15 is high. If it is high here, then the output here in the inverter would be low. I mean, the output in the inverter at the bottom will be low. Yes. So if it is low, it enables the RAM. So it says, RAM, you are selected. And the RAM will place the data from its cell number. Says the cell number is some 1234x1234. Okay. And it will place on the bus because now A15 is not the part of the address bus. RAM only sees this thing. It doesn't see this thing. It only sees the binary stuff. So what is related to it, it places its address on that particular address cell. Or from its cell number, it places onto that particular address on the bus. Got it? You can just go through this slide again and again. I told very clearly the connections and all what is done. If A15 is 0, RAM or ROM will activate. If A15 is 1, RAM or ROM. If A15 is 0, the ROM is considered. And if A15 is 1, the RAM is considered. If the A15 signal would be high, then the ROM is disabled. And the A15 in the RAM gets low signal and it would be enabled. And the cell number is, if the data is placed in the particular address and RAM only sees this particular binary format, it doesn't look into this particular one. I hope you're pretty much comfortable with this particular lecture video, and I'll just stop this lecture video here. In the next lecture video, I'd start teaching you the direct memory access, the interrupt latency, and the shared data problem, and that's the end of the first unit. So thank you guys.